Let's talk about the work-energy theorem. We previously learned that energy cannot be created or destroyed. It only changes forms due to the law of conservation of energy. So how can an object gain or lose energy? When work is done on that object. So remember, work is the only way that energy can be transferred to or from an object or a system. So positive work means that object is gaining energy. Negative work means the object is losing energy. So what we can do here is we can actually write an equation for this. And this is called the work-energy theorem. So the change in energy is equal to the work done on the object. So that means in terms of equations, our delta E, or our change in energy, is equal to work. Now, again, we can see here that if we have a negative work done on the object, then we're going to decrease in energy. If we have positive work done on the object, we will increase in energy. Again, that delta means final minus initial. So we have energy final minus energy initial. Now, usually when we're using this equation, we use it with kinetic energy. So usually you will see a work kinetic energy theorem equation, and that's just the change in kinetic energy is equal to the work done on the object. So we get delta K, which is kinetic energy final, minus kinetic energy initial equals the work done on the object. Now, that's not to say that something can't increase or decrease the potential energy of an object as well. So I'll talk a little bit more about that later. But like I said, usually we're talking about increasing or decreasing kinetic energy. And then if we solve for final kinetic energy, what we get is initial kinetic energy plus the work done. So again, we can see if we have a positive work on the object, we're going to increase in kinetic energy. If we have negative work done, we will decrease in kinetic energy. Now, when we have something like the gravitational force, we might be, say, throwing a ball up into the air, and then as that ball rises up in the air, the kinetic energy is decreasing, right? Because velocity is decreasing. If it's going straight up and straight down, the velocity decreases to 0 at the very top, and we have all gravitational potential energy, and then it turns around, and then that velocity is going to increase as the ball falls back down. Now, what's happening here is the force of gravity is doing work on the object as it rises and as it falls. So the work done, remember, is force times displacement times the cosine of theta. That's the equation for work. So what we get here, we know that the force of gravity is equal to the mass times acceleration of gravity, mg, and then that will be times displacement for the work times the cosine of theta. Now, again, if I draw my force of gravity into this little figure on the right-hand side here, I can see that that force of gravity is always directed downward. So remember, this theta right here, that's the angle between the force and the displacement. So because of that, I know displacement as we go up is going to be upwards. So we can see the force of gravity is down as we move upwards. The displacement is upwards. So that angle right there is 180 degrees. Now, after we get to the top and then we're going back down, the force of gravity is in the same direction as the displacement. So that angle right there is 0 degrees. And this will have to do with the sign of work that's happening on the object. So for a rising object, like I said, on that side where it's going up, the force of gravity is directed opposite the displacement. So that angle is 180 degrees. Now we know that the cosine of 180 degrees is -1. So what we get here is that the work done on that object is the force of gravity, mg, times the displacement times the cosine of 180. So what we get is a negative mass times acceleration of gravity times displacement. And this tells us that because there's negative work done on the object is losing kinetic energy. And we know that it is losing kinetic energy because it slows down as it goes up into the air. So like I said, negative work, we have a decrease in kinetic energy. Now, as that object then falls back down to the earth, then the force of gravity is in the same direction as that displacement, and our angle is 0. So we get the work done on the object by the force of gravity is equal to the force of gravity, mg, times the displacement times the cosine of 0. The cosine of 0 is 1, so our work done is at a positive maximum. So we get a positive mass times acceleration of gravity times displacement. So here, because our work is positive, that means we're increasing in kinetic energy. And we know that that's true because we are speeding up as that ball falls down towards the ground. Now, if we're lifting or lowering an object, we don't just have the force of gravity anymore. We also have an applied force upwards, okay? Now I can't speak. If that applied force is either positive or negative, or the force of gravity is positive or negative, that will depend on the direction of displacement, okay? When we're talking about the work done by those forces. So what we get here is we know that the net work done on this object is equal to a change in kinetic energy. Change in kinetic energy, of course, is kinetic energy final minus kinetic energy initial, and then the net work will be equal to the applied work done by the applied force plus the work done by the force of gravity. Remember, when you're adding two works together, all you do is add them together because this is a scalar quantity. Of course, one of those things is going to be negative in this case because it really just depends on the displacement. But if it's in the same direction as displacement, if the force is, then that work will be positive. If it's opposite direction than displacement, then that work will be negative. So like I said, that W sub A is the work done by the applied force, and then W sub G is the work done by gravity. And then those signs, like I said, of WA and WG depend on whether the object is being lifted or lowered. So here this object is being lifted, and I can see that the applied force is in the same direction as displacement. So that means the angle is 0, and therefore that's a positive work done on that object. The force of gravity, though, is 180 degrees in relation to that displacement, and the cosine of 180 is -1. So we get a negative work done by that force of gravity. If we're lowering an object, then the applied force is 180 degrees from the displacement, which means that is the negative work. And then the force of gravity is in the same direction as the displacement, and cosine of 0 is +1. So that's the positive work done by the force of gravity when you're lowering an object. Now, here's a special case here, is that if your object is stationary before and after a lift, and we're going to actually use this scenario when we do a little lab next week, I think it is, with, I call it the Human Work and Power Lab. And in that lab, you will run upstairs, or I have a video of myself doing it. And if you start at rest, and then at the top of the stairs, you end at rest. So this is an example of that. If an object is stationary before and after a lift, or before and after you run up the stairs, then the kinetic energy final will equal the kinetic energy initial. Because again, you start at rest, you end at rest. Doesn't really matter what happened in between that. The kinetic energy initial equals the kinetic energy final, and those are both 0. Now, also, if you have, say, an initial velocity equal to a final velocity, maybe not 0, but something else, then kinetic energy initial will equal kinetic energy final. So that's just another scenario. Now, what happens here is that because we know that work is equal to a change in kinetic energy, what we get here is that the work done by the applied force plus the work done by the force of gravity is equal to 0. Now I have a negative here in front of the work done by the force of gravity, because if you're going up, your displacement is up, right? And that means that that force of gravity, that force vector, is down. So that angle between the displacement and the force of gravity is 180, which means that you would get a negative work done by the force of gravity. So I just plugged in that negative right there. So if I solve for the applied force here, I just get that the applied force is equal to the work done by, the work done by the applied force is equal to the work done by the force of gravity. And then of course we know the work done by the force of gravity is the force of gravity, mass times acceleration of gravity, times the displacement, times the cosine of theta. So we plug that in for the work done by the applied force. And this is only if your initial and final kinetic energies are the same. Now here what we can see is that we have something very interesting, right? We have this right here, mgd, that looks really familiar. Well, it's like an mgh if we're talking about, say, going straight up, right? Mass times acceleration of gravity times a height. And so here what we can see is that the work done on the object is increasing the object's potential energy. All right. So like I said before, this work done on the object can either increase the kinetic energy and or increase the potential energy. We just have that kinetic energy work theorem because a lot of the time we talk about an increase in kinetic energy. But here we're increasing potential energy by the work done by the applied force.